You know the drill, right? You clear out a space in your living room, you strap on the latest VR headset, and for the first, I don't know, 15 minutes, it is pure magic.
Oh, absolutely. It's
Yeah,
incredible.
you're like walking on Mars, or you're manipulating these 3D architectural models with your bare hands. The visual fidelity is just, it's flawless.
Right.
But then right around that 20-minute mark, something shifts.
Yep. The honeymoon phase ends.
Exactly. It starts as this really subtle pressure behind your eyes, maybe a slight clamminess, and before you know it, your stomach is just doing flips. The digital world still looks perfect, but your very physical biology is loudly demanding that you lie down immediately.
It is the great paradox of the immersive tech industry right now. I mean, we've engineered these displays that can absolutely fool the visual cortex,
Right.
but we haven't been able to fool the inner ear or the autonomic nervous system or really the intricate musculature of the human eye.
Wow, yeah.
The hardware is basically writing checks that human physiology simply cannot cash.
That is perfectly put. Well, welcome to the deep dive. We have a genuinely fascinating mission today. We are looking at a newly published patent open framework draft that just dropped on Zenodo on April 19th, 2026.
Fresh off the press.
Totally. It's called the VR Fatigue Biosensor Framework. And this is authored by Dr. Melvin Sewell, who is affiliated with both TrueFlow Games and the Cosmic University of Echo Rift Studies.
And this document provides a really unique perspective because of its origins, actually.
Right. It didn't start out as a normal paper.
Exactly. This didn't begin its life as a purely academic, theoretical thing. It's actually a complete reframing of a National Science Foundation SBIR phase proposal.
Oh, wow.
Yeah, so Dr. Sewell essentially took a business-oriented, commercialization roadmap and transformed it into a rigorously structured scientific record for the Zenodo archive.
That's wild.
It really is. We're basically seeing the exact intersection where commercial product development runs headfirst into hard biomedical science.
Okay, let's unpack this. The core problem this framework tackles is making immersive VR environments actually habitable for long-term use.
Which is the holy grail right now.
Right. I mean, we hear endless talk about the metaverse, virtual office spaces, 8-hour digital classrooms. But the reality is VR fatigue, the eye strain, the nausea, that profound disorientation.
The dreaded VR hangover.
See, yes, that is a massive physical roadblock preventing any of that from becoming mainstream.
It really is. And the primary culprit driving this fatigue is a physiological mechanical failure known as Vergence Accommodation Conflict, or VAC.
VAC. Okay, let's break that down for the listener.
Sure. So, to understand why VR makes people sick, we have to look at how our eyes operate in the physical world. It's a dual action process. When you focus on a physical object, your eyes converge.
Meaning they sort of angle inward?
Exactly. They physically point at the target. But simultaneously, the crystalline lenses inside your eyes accommodate. They actually change shape to bend the light and bring that specific distance into sharp focus.
Right, okay. And in the real world, those two actions, the vergence and the accommodation, they're neurologically hardwired together.
Yes, completely coupled.
Like if I hold my hand up near my face and look at it, my eyes cross slightly and my lenses just immediately adjust to a close focal depth.
Instantly. You don't even think about it.
But strapping a VR display to your face kind of shatters that neurological coupling.
It creates an impossible situation for your visual system because the actual VR screen is fixed at a static distance from your cornea,
Yeah.
usually just, a couple of inches away.
Right.
But the lenses in the headset use optics to push that focal plane out to a fixed distance, say 2 meters.
Okay, I follow.
So your eyes are constantly accommodating or focusing
Yeah.
at that static 2-meter distance. But the digital objects rendered inside the simulation are constantly moving around.
I try to picture it as this physiological tug of war.
That's a great way to look at it.
Like, the simulation is telling your brain to converge your eyes on a virtual mountain that looks like it's a mile away. But your lenses are being forced to maintain focus on a display that is fixed right in front of you.
Exactly.
Your brain is receiving completely contradictory data streams.
And the visual cortex just cannot reconcile that conflict. So the brain interprets these contradictory sensory inputs as a sign that something is deeply, deeply wrong.
It panics.
Basically. It defaults to an evolutionary defense mechanism. It actually assumes you've ingested a neurotoxin.
Wait, really? It thinks you're poisoned?
Yeah. And that is what triggers the nausea and motion sickness. Your body wants to purge the poison.
That is insane. Now, looking at this from a pure, software design perspective, you might wonder why we need an elaborate biosensor framework to fix this at all.
Right, the old just ask them approach.
Exactly. We know the user feels sick. The obvious low-tech solution would just be to implement a digital wellness check.
Just a little pop-up.
Yeah, program a pop-up into the VR software that pauses the experience every 30 minutes and just asks, hey, on a scale of 1 to 10, how much eye strain or nausea are you experiencing right now?
Which sounds logical on paper, but the framework actually addresses the inadequacy of subjective methods right out of the gate.
Why is it inadequate, though?
Because relying on self-reporting is fundamentally flawed in highly immersive environments. Cognitive load plays a huge role here.
Meaning how distracted they are.
Exactly. When a user is deeply engaged in a complex task, say like a high-stakes training simulation or a really fast-paced game, their conscious awareness of their own physiological state drops significantly.
Oh, that makes sense. They're just too focused on the game.
Exactly. By the time the user consciously registers that they're nauseous and actually clicks yes on a subjective questionnaire, the physiological cascade has already happened.
It's too late.
Way too late. The fatigue is set in, and the session is effectively ruined.
Not to mention, pausing a simulation to ask someone about their stomach completely destroys the immersion. It's totally jarring.
You're snapping them out of the digital environment to violently remind them of their physical constraints.
Exactly.
So if we can't rely on self-reporting, and we obviously cannot hook a consumer up to a multi-node EKG machine in their living room, we have to find a way to monitor their distress invisibly.
Which leads us directly into the hardware stack Dr. Sewell outlines.
Yes, the hardware stack. This part is super cool.
It really is. The instrumentation relies on integrating clinical-grade monitoring into form factors that consumers already accept.
Right. So the framework utilizes this highly specific multimodal wearable setup to continuously monitor the user without requiring any active input from them.
Seamless integration.
The stack consists of two primary components. First, there are eye tracking glasses integrated with infrared sensors to monitor pupil size and gaze behavior.
Yep.
And second, there is a physiological wristband. And this is not just tracking steps like a normal smartwatch, right?
Much more advanced. It's using photoplethysmography, or PPG, to monitor heart rate, alongside sensors for galvanic skin response, or GSR, to measure skin conductance.
What's fascinating here is the absolute necessity of that multimodal approach.
Yeah.
From a biomedical engineering standpoint, relying on just one data stream in a dynamic environment like VR is virtually useless.
Why is that?
Because the data is incredibly noisy.
Because context matters.
Exactly.
Like if a wristband detects that my heart rate just spiked to 110 beats per minute, it doesn't inherently know why. Am I experiencing the onset of VR nausea, or did a virtual monster just jump out of a closet in the game?
Precisely the issue. Cardiovascular data alone cannot differentiate between excitement and actual physical distress in a simulated environment.
That is a huge distinction.
Huge. But when you synchronize the data streams, you can isolate the specific physiological signature of the version's accommodation conflict.
Okay, let's break that down. Let's look at the eye tracking first.
Sure. So the infrared sensors allow for continuous monitoring in the dark interior of the headset. They're tracking these micro fluctuations in pupil dilation and erratic saccadic movements.
Saccadic movements being like the twitchy eye movements.
Yes, the rapid jumps your eyes make.
Mm-hmm.
When the ocular muscles fatigue from that constant tug-of-war we discussed earlier, the pupil's response latency actually changes. It gets sluggish.
Oh, wow. And then you layer the galvanic skin response on top of that.
Right.
So GSR is measuring the electrical conductance of the skin, which fluctuates based on sweat gland activity.
Exactly.
And since the sweat glands are directly controlled by the sympathetic nervous system, our fight-or-flight response, GSR, acts as this incredibly sensitive indicator of autonomic arousal.
Essentially a stress detector.
Right. So even before you consciously feel a cold sweat coming on, the onset of motion sickness triggers a microscopic increase in moisture on the skin. And the wristband detects that as a spike in electrical conductance.
And you also have a PPD sensor on the wristband analyzing the volumetric changes in blood circulation.
So, the heart rate.
Yes, but the framework isn't just looking at the raw heart rate. It's looking at heart rate variability, the time intervals between individual heartbeats.
Oh, I've heard of that. HRV.
Yes. A sudden drop in heart rate variability combined with rising skin conductance and that erratic pupillary response we talked about.
It paints a picture.
Exactly. It forms a very clear multi-axis picture of a user entering physiological distress.
But wait, this introduces a massive data problem, doesn't it?
Oh, absolutely.
Collecting pupil dilation metrics, sweat gland conductance, and microvariations in heartbeats that generates an overwhelming amount of raw biometric data.
Mountains of it.
And raw data is inherently messy. You can't just code a simple threshold rule that says, hey, if sweat equals X and heart rate equals Y, trigger the alarm.
No, human physiology is way too complex for basic if-then statements.
Right. So how does it handle all that noise?
That is where the software layer of Dr. Sewell's framework becomes the true engine of the system. The raw signals undergo rigorous pre-processing.
Like filtering.
Yeah, filtering out motion artifacts. Like if the user is just aggressively swinging their arms around playing a game, and then the system extracts the relevant features.
Okay.
These clean data streams are then fed into a deep learning architecture.
Ah, the AI component. The deep learning algorithms are what elevate this from just a simple monitoring tool to a predictive engine.
Precisely. The AI is trained to identify complex, nonlinear relationships across all these distinct physiological signals simultaneously.
A nonlinear pattern. What does that look like in this context?
It means the algorithm is looking at how variables interact dynamically over time. For example, the AI learns that if skin conductance rises exponentially, while the heart rate drops slightly before spiking, and the pupillary response becomes sluggish,
All at once.
all within, say, a 10-second window. The AI knows that specific temporal pattern has a 95% correlation with the onset of VR fatigue.
That's incredible.
The deep learning model is constantly inferring the user's cognitive and physical load. It's essentially diagnosing the nausea before the user's conscious brain even registers the discomfort.
Wow. Okay, here's where it gets really interesting.
Yeah.
Because diagnosing the fatigue is only half the framework. The biosensor doesn't just act as a silent observer that eventually tells the software to just, shut down.
Right, that wouldn't be very helpful.
Once the AI detects that the user is slipping into the early stages of fatigue, it actively intervenes through what the paper calls adaptive feedback.
The system creates a real-time, closed-loop intervention.
Closed loop, meaning it adjusts itself.
Exactly. The Biosensor communicates with the VR engine and demands instantaneous adjustments to the virtual environment across multiple sensory channels: visual, auditory, and haptic,
And the goal is to dynamically reduce the mechanical strain on the user's body.
without them even knowing.
Let's dig into the mechanics of that mitigation, starting with the visual feedback. How does the system actually tweak the environment to stop that ocular tug of war?
So the framework outlines techniques like dynamically adjusting the depth of field.
Okay, blurring things.
Yes. If the biosensor detects rising fatigue, the rendering engine might softly blur the background of the virtual environment.
Why does that help?
Well, by removing the sharp details of distant objects, the system removes the visual stimulus that's forcing the user's eyes to diverge.
Oh,
It subtly forces the visual system to relax its vergence and focus on the foreground, bringing the user's physical eye alignment much closer to the actual focal length of the VR display.
that is incredibly clever. The system can also implement dynamic field of view reduction, right?
Yes, the vignette effect.
Essentially creating a subtle black vignette around the edges of the screen during high motion sequences.
Exactly.
Restricting peripheral vision is a proven method for reducing motion sickness because the periphery is highly sensitive to the optical flow that causes that spatial disorientation.
Yes, the visual rushing effect.
But I have to push back on this a little bit from the perspective of the software developers and the digital artists.
I know where you're going with this.
Right. Like, if I spend 4 years designing a meticulously detailed, visually breathtaking virtual world, the last thing I want is a background algorithm suddenly blurring my textures or throwing a black vignette over the edges of the screen just because a user's wristband detected some sweat.
It's a valid concern.
Doesn't this adaptive feedback completely compromise the artistic intent of the VR experience?
It is definitely a significant tension point between biomedical engineering and experiential design, but the framework explicitly addresses the need for subtlety.
Subtlety is key here.
Right. The threshold for these interventions is designed to operate just below the user's conscious perception.
So they don't even notice the vignette.
Exactly. The vignetting might only reduce the field of view by 5 or 10% during a rapid camera pan, and the depth of field blur is applied specifically to areas outside the user's immediate foveal gaze.
Oh, so only the parts they aren't looking directly at anyway.
Right. The argument from the biomedical side is that a slightly blurred background for 30 seconds is vastly preferable to the user ripping the headset off and abandoning the software completely because they feel physically ill.
That's a fair point. It's a trade-off between absolute visual fidelity and actual usability.
Exactly.
And the framework doesn't just rely on visual tricks either. It utilizes auditory and haptic feedback to physically ground the user.
This is a huge component. The
Yeah.
vestibular mismatch, that disagreement between your eyes and your inner ear, is incredibly disorienting.
Right.
But by introducing spatial auditory anchors, the system can provide a fixed acoustic horizon. That gives the brain a stable reference point, even if the visual environment is spinning around wildly.
That's brilliant. And the haptics play into that as well, don't they?
Yes, they do.
The framework discusses using the wristband or the handheld controllers to deliver specific rhythmic vibrations when fatigue is detected.
Rhythmic is the key word there.
So if your visual system is telling your brain that you are flying through space, but your inner ear is saying you are sitting in a chair in your living room, a rhythmic haptic pulse on your wrist provides a third grounded data point.
It's a tiebreaker for the brain.
Exactly. It gives your nervous system a tangible physical sensation that anchors your spatial awareness back to your actual body in the physical room.
It's a remarkably comprehensive mitigation strategy.
It's about the flow.
You're engaged in the simulation. Your autonomic nervous system begins to stress.
The deep learning model flags the nonlinear biometric signature.
And then the background subtly blurs to relax your ocular muscles. A rhythmic haptic pulse grounds your spatial orientation, and your physiological distress naturally subsides.
All seamlessly.
Ideally, yes.
Hmm.
All of this happens without you ever realizing the system intervened at all.
It acts as a completely invisible subconscious safety net.
That's the dream.
But as we look at this framework, we do have to ground it in reality. I mean, this is a scientific draft based on an NSF phase-I proposal. The technology is not currently integrated into every consumer headset on the market.
If we connect this to the bigger picture, the paper is very transparent about the current boundaries of the research.
What are the main limitations right now?
Well, the preliminary prototype results are highly promising. The multimodal sensor fusion, combined with the deep learning classification, demonstrated a very high degree of accuracy in detecting and mitigating fatigue in a controlled environment.
Right.
But the framework acknowledges a critical limitation that must be overcome, and that is the necessity for massive, large-scale validation studies.
Because human physiology is not a monolith.
Not at all.
Like, training a deep learning algorithm on a dataset composed entirely of 25-year-old gamers is going to yield a model that fails spectacularly when it's applied to a 60-year-old architect who's using VR for structural design.
The demographic variables are immense. Think about it. Baseline heart rates vary wildly based on age and cardiovascular fitness.
Oh, true.
Skin conductance baselines differ drastically. Intercupillary distance and ocular muscle strength change dramatically across different populations.
So the algorithm would get confused.
Exactly.
Yeah.
For this adaptive feedback loop to be safe and effective, the AI models require vast, diverse data sets. That's the only way to ensure the system accurately interprets the physiological signals of all users, regardless of their individual biology.
So what does this all mean? Why does a framework draft sitting on Zenodo matter to you, the listener, or to the broader landscape of technology?
It's a paradigm shift.
It really is. It matters because it represents a fundamental shift in how we approach human-computer interaction. For decades, the burden of managing physical limitations in digital spaces has fallen entirely on the user.
Right. You feel sick, you take off the headset.
Exactly. You get a headache, you turn off the screen. It's on you. But Dr. Sewell's framework shifts that burden from the human to the machine. It envisions a paradigm where the digital environment is actually responsible for adapting to the biological constraints of the user.
And if the industry wants to move beyond novelty experiences, building immersive environments where people can comfortably work, learn, and socialize for extended periods,
Which is the goal.
then solving the physiological bottleneck is non-negotiable. This multimodal, closed-loop system provides a highly rigorous, scientifically backed roadmap for achieving that sustained usability.
We started out talking about the old sci-fi fantasy of leaving the physical body behind to enter virtual worlds. But the reality this framework exposes is that the body actually remains the ultimate anchor.
You can't just leave it behind.
You cannot escape your physiology. You can only build systems sophisticated enough to accommodate it. And that leaves us with something to think about.
It really does.
If this level of biometric integration becomes the standard for interacting with immersive technology, imagine a future where the digital worlds we inhabit are constantly monitoring our physical limits in real time. What happens when our entertainment and productivity devices start managing our physiological well being better than we do ourselves?